Okay, hello everyone. Good afternoon to you all. I hope you've been enjoying Cisco Live so far. Welcome. This is Containers and Microservices, a Survival Guide. So I'll just give you a quick introduction to myself. I'm Stephen Tallamy. I'm a cloud architect within the service provider video group, but I'm not going to be talking anything really about service provider video, but I will be talking a lot about these kind of things that I spend my time. The cloud bit generally means I'm thinking about some of these technologies and using them as well in reality. And so I'm very happy to be here at Cisco Live in Orlando. Orlando's a place of one of my other favorite places in the world, which is Disney World. So just quick show of hands in the audience. Who here has been to Disney World at least once in their life? So a pretty decent show of hands. Who's been to Disney World since they arrived here at Cisco Live? Good effort, that man. Well done. Oh, Tess, nicely done. Excellent, well done. Who's been to Disney World without kids? There's a few. And who's been to Disney World with kids? Quite a few more, right. So just for those who haven't been, done it one of these other styles or not been at all, there's kind of a bit of a difference between going to Disney World with kids and without kids. And bear with me, there is a point towards containers coming. So, so I've done both. I've been to Disney World with or without kids, and so let's take a day out to Epcot. This is what it looks like without kids, right? So you kind of wake up, you have a light breakfast, and you drive to the park, and you get there pretty early. There's loads of space in the parking lots. You kind of get on the nice little courtesy tram, and you arrive at the front gate as an Epcot, go and have a look at all the nice, the nice entrance, and then you kind of plan your way around the showcase lagoon, thinking about the nice things that you're going to eat. You can go to China, maybe you can get some sushi in Japan, you can trial all the, maybe the beers and stuff all the way around. You spend a nice time sort of planning that out. That's what it looks like when you don't have kids. When you do have kids, there's a bit of a different picture. So in the morning, instead of just kind of waking up, you've got to do they've got to get their lunch packed because they may not eat everything. You've got to get lotion on it. I've got 4 kids. 4 kids with lotion. Oh my God, it's just a complete nightmare, right? And then you're about to get in the car, you leave, then you've got to go back because somebody left their cuddly toy that has to go to Disney World. And eventually, instead of the car park looking like that, it looks a lot more like this. It's full of cars, right? And you end up parked all the way down the other end. You've got to then walk all the way. The tram's out of the question now because you've got your stroller, right, which is full of crap that you've got to bring for the kids. And, so there's no chance of enjoying that. And then, of course, you get to the entrance gate. Well, Mommy, Daddy, I need the loo. Why didn't you go to the toilet before you left? So you're off to the restrooms. And then, you're just looking for the one restaurant that does both burgers and chicken nuggets because that's what the kids will only eat. Right. Totally different experience. Well, what am I talking about? Actually, in fact, that's why there are blog articles like this, like Parent Survival Guide to Walt Disney World. How do you survive going to it? And there's a few things, definitely, if you do go to Disney World with kids, get these things. They're magic bands. They might seem like a bit of a gimmick, but once you've given your ticket out to your kid enough times and then handed it back again, just having something they can scan, brilliant thing. So, but now back to technology, just sort of a slight digression to Walt Disney World. Let's take a look at technology. Because a lot of people here, hopefully, are starting to plan a trip to Containers World, which is where dreams come true as well. So another quick show of hands in the room. Who here is sort of developing microservices in their organization? Or they've got people? Not many. Oh, a few. How many, another show of hands, who's actually deploying microservices in containers? Even less. So I kind of want to say to you that, when you're developing containers, it's kind of like going to Disney World without the kids, right? It's great fun. You're getting all the benefits out of it. And deploying is a bit more like going to Disney World with kids. You've got all that other stuff going on that you've got to kind of deal with to get it into production. And so, my main takeaway point today, and we're going to continue to see this analogy, is that taking microservices and containers into production is like visiting Disney World with kids. You need a survival guide. And that's what I hope to give you today, is that, or parts of that survival guide. And we can continue the conversation in the WebEx room as well afterwards. So hopefully you've seen the agenda already ahead of the session. So these are what we're going to look through, the sort of the whys, the hows, and then how some good practice is going to set you up for surviving containers and microservices and so on. So that's kind of like, that's what we're going to walk through. And what I want to start off with is the why. And I think it is important to understand, just to survive, why you're going to do this. Why am I going to create microservices? Why am I going to create containers? What is the point of all of this? Because first off, you've got to understand it yourself, but you've also sometimes having to sort of justify why they are being used within your organization. They'll say, well, why are you doing this? Why do we need to make this change? So let's just go through a little bit of this. First, a couple of definitions. In case you're not familiar with containers or microservices, here are a couple of good definitions. So a container wraps a piece of software and all of its dependencies, so all the things that it needs to do its job, into one object that can be moved around and run on a shared kernel. So you can have multiple containers running on that same shared kernel, and there is isolation then between the different containers running on that kernel. So that's what a container is, and we'll go into a lot more detail about how do they build up and what that means. Microservices is a bit of a looser definition, but I got this one from Martin Fowler, who's quite well known in the industry. So it's all about developing an application as a suite of small services. And I think some people don't actually get this point. When they kind of first come across microservices, they just think that they're going to have this one dumb little service that doesn't, interact with the world. You've got to think about it as a suite. You're going to have things cooperating with each other. And where, previously those things were cooperating within one sort of monolithic application and doing all of the process calls inside that one application. Now we are splitting that apart, and those microservices are talking over the network, and they're usually using HTTP. Okay, so for anyone who's kind of coming from a networking background, you're going to see a lot more of the processing that's going between the applications that are making up your services. So those are the two quick definitions, and let's have a look at some of the drivers or some of the challenges that we sort of face now as we're sort of rolling out applications now that are sort of motivating the move towards these microservices and containers. So one of them is this feature-driven challenge. Now the feature-driven challenge is this is actually an example from the video space that we had. So we had a content search engine where you'd ingest all of your data about the TV schedule, so all your channels, all your times, and all of your VOD assets, your catch-up, your on-demand catalog. You ingest that into it, and then it would provide a kind of range of different search options. And what you find then is taking a feature-driven approach. So I want to deliver a feature at a time and deliver that and roll it out. You find you end up doing this. You go, well, I want to add the ability to see the likes of a particular piece of content, let's say X Factor, in my application. So I create an API, and somehow I get all of the Facebook pages ingested into my system and somehow link them to all that other content. And that's okay. It's getting a bit out of hand, but it's okay. But if you then continue to expand this monolithic application to say, well, now what I want to do is I want to show the user all of the shows that their friends like on Facebook. So all of the things that they are interested in, I want to show them inside my TV application, so they've got sort of a kind of social recommendation. You can see that ingesting the whole of the Facebook social graph is just, we're out, this pattern isn't fitting anymore. And trying to fit into this same API is just not happening either. So as you go through this sort of trying to implement and add new features to your platform, you kind of get in a bit of a trouble if you continue to have this one monolith. And each of these things are going to scale differently. So it's kind of better if you can kind of think about how you break these things up. And this is exactly what we did. We sort of broke them up into microservices. So one that was dealing with schedule, one was doing VOD assets. If we wanted to do the social lookup kind of thing, that would be its own service that would ingest it. And maybe if we had a social recommendation, instead of doing the ingest thing, we'd go out to Facebook and kind of go query that data and then kind of join it together. So that's one of the challenges that sort of drives you towards breaking down that monolith into smaller services or microservices. Another one is a scale challenge. So this is another example from the video space. This is from our cloud DVR solution. And so this is responsible for, in the cloud, just like your home DVR might do, it makes a recording. You say, I would like to record this thing on this channel at this time. And this does it in the cloud for you, stores it on a disk in the cloud, and then you can play it back at some time in the future. And we actually designed that CDVR, Cloud DVR solution around microservices so that we could scale. Because we've got different scale factors there. We've got scaling around the numbers of channels. So as providers start to roll this stuff out, sometimes they might start with just their premium channels they're going to offer this for, and then they'll sort of expand it out to all the shopping channels and other things that maybe people might want to record. I don't know why, but so they'll sort of expand it. So that's one kind of dimension of scaling. But then you've also got the number of recordings you're going to need to make, right? So how many people are actually booking recordings if everybody's recording the same thing at the same time? And you've got a different scale. And then you've kind of got to play out one. How many people are actually going to play out their recordings from the cloud and how often and so on. And so each of these individual parts, if we'd made one big monolith, it would have been very difficult for us to scale these solutions out, and hence, again, breaking them into microservices and actually deploying them using containers is giving us that ability to scale out. So another challenge we keep hearing, the multi-platform challenge. You want sort of one kind of way in which you can deploy your application across multiple different clouds, maybe on-prem. So you need one kind of place, one way in which you can simplify all of that and have one unit that you can deliver into each of those. And containers provide us with a great way of getting to that. And then another sort of maybe slightly future-looking thing, when you have all of these connected devices wanting to access services, you start to get towards the sort of edge computing kind of scenario where you need ultra-low latency responses so that your train systems or your home automation systems or whatever it is, or even voice recognition. And sometimes you've got virtual reality where you've got very high bandwidth requirements. You can't be sending that up all to a centralized cloud. And so you start to need these edge compute available, but you still need to manage those applications. And so when we've looked at edge applications in the video domain, we found that containers provide us a great way of taking an application and sending it out to a device that might be somewhere way out on the edge with not a lot of central management capability. So we've actually used the Kubernetes framework that works along with containers to achieve that kind of thing. So that's another kind of challenge that we face that starts to drive us towards containerization, microservices as well. And there's a whole kind of host of benefits that you start to see in terms of the way in which you can deploy. So you can reduce your deployment footprint if you can combine multiple things onto the same virtual machine. You can get a kind of natural sort of compaction of those things. You've got that repeatability. A container is actually something, as we saw, it's sealed with all of its dependencies. It means that it comes with all that stuff so that when you go and deploy it, if those stuff you don't need to worry about, or have I got the right version of Java or Node.js or whatever it is, that it's all there available. Containers are lightweight, they spin up very, very fast. So you get a whole kind of host of these things kind of available to you as you start to do it. And I kind of summarize these sort of like, it's about reducing the total cost to develop, operate, and maintain a service. Right? So that's one of the real big benefits that you start to see. And I kind of deliberately put that total cost thing out there because you will may get some small cost savings from, if you're hosting in a cloud, you may get some reduction because your containers are smaller units and you can pack them together onto virtual machines. But it's that total cost. It's like, well, how, in terms of the amount of time you're debugging these things and deploying these things, if you can spin these things out very, very rapidly, your costs can go down quite significantly. But it's also increasing that feature velocity side of things. So you are able, because you've got now these tools and these abilities, you can actually get your features out there a lot faster because you know that they're going to be repeatable, they're going to be, spin up in no time at all, and you've got that consistency because when you create the container, that container can work on the developer's machine exactly the same as it will run in production. And that is a really important thing. It's not something changing. We've got a question here. So the question here, the question here was, is the app on top of the OS on top of the container? I will answer that question actually in the how containers work section. So it's just upcoming. So this is kind of like the drivers, and I think it's important, as I was saying before, it's important to get into a position where you can describe these benefits, all of these benefits to people, because often you're going to get challenged along the way. Well, why are we doing this? What are the reasons? What are some of the points of doing this? What are we trying to achieve? And also it's a good way actually of measuring if you're achieving those benefits, because if you are finding that actually your deployment times are not going down, then perhaps you haven't gone about it the right way, and you need to go and find out and figure out why that you're not realizing that benefit. So why use, just in kind of summary of this section here, kind of why are we using containers? It's about that feature velocity, being able to independently scale things, having that multi-platform, even edge computing solution, but also trying to reduce the overall total cost. And I'm just going to pause each of these sections. I'm going to pause and see if there are anyone who's got any questions on that section on the kind of why we might be using these things. Is this stuff that people kind of heard before in terms of why, the motivations? Seeing some good nods around the room. So it's kind of familiar with the why we would do this. But it is important to remember it and kind of go back and look at it. Because, again, in terms of the overall survival guide, if you don't kind of know why you're doing this thing, you don't know how to survive, or why should you even bother trying to survive in this new and changing environment if you haven't kind of embraced this piece. So is there any questions at all on this bit? I expect more probably when we get into the detail. Okay. So how containers work. Let's go and have a look at how a container actually performs. I'm not going to do this with microservices because they're kind of a bit more of a higher level, application, and it's very specific, often to a language. But let's go and look at containers themselves and how they actually work. So there are actually two things that are the foundation of how a container operates, and these are control groups and namespaces. So these are actually technologies that have been built into the Linux kernel for a very, very long time. They've been used in different ways over a period of time to sort of isolate things out. So when you've had these sort of shared hosting environments and some of these things sort of come to play, but a container sort of brings them together in a very useful and portable way. So yeah, the control groups are there because if you remember from the definition, you need to be able to have these things running on a shared kernel, so you don't want one of them going off and taking all the memory or all the CPU or any of the other resources. But you've also got it said it's also as isolated. Right? Isolation. That isolation is really key and important there, and so that's what the namespaces bring. So let's go and have a look at some of those, some of these details into these. So control groups. These are kind of like your most common control groups that you have built into the system, and really the key ones that you're going to be seeing generally are the control groups around CPU and memory, and then slightly less in the world of storage and networking. And those ones are coming and being used slightly more, but perhaps generally if you look at the technologies like Docker and Kubernetes, they have bits that can kind of touch to these, but they've mostly been focused in the first part. And I hopefully these things will also come into play. And if you want to find out more about some of the things Cisco is doing in this area, then we have the Contive project, which is part of the container Cisco container platform. So what is these all about? So the CPU C groups are there to basically give you a share of the CPU. You could have an entire CPU or multiple CPUs or some percentage of a CPU. And particularly if you're doing lightweight microservices, then hopefully you're kind of finding that you're just only needing a fraction of a CPU. So you can kind of ask for certain allocation of CPU. And of course, memory as well. How much memory do you need to reserve for this process just to work in the first place? It needs a certain amount to keep going, and then what's the maximum memory? And what the Linux kernel does is it then enforces these things on the container. From the perspective of the CPU, if you hit the amount that you've asked for, so you've asked for 2.5 CPU and you start trying to go above that in terms of the amount of CPU usage, it's just going to limit you. It's just going to keep time slicing you down to 2.5, and so your process will not be able to go any faster. If you hit the maximum memory, it's just going to kill the process completely. Right? So as soon as you hit that memory, you're done. You're out. And that's deliberate, because typically the memory sort of challenges there are memory leaks. Right? If you can't guess how much memory you're going to need, you've kind of got a memory leak. Or you're going to need to sort of scale out in a horizontal way, and we'll talk a little bit about the way in which you can achieve that kind of scalability. So these are the top two are the ones that kind of we see the most in terms of control groups. The namespaces. So again, when you actually have a container running, it's going to get its own isolated network, and we'll look at how that network hangs together in some of the later slides. So it gets its own. So when I'm running my container, it feels like I'm in my own network space, and I can do what I need to in there. I've got my own process space, so my container cannot see other containers' process spaces. Its own file system mount points. So again, it can't see the whole of the host file system. It just sort of sees a virtual file system inside of it, and a few other kind of pieces. So each of these things, these namespaces, get created inside of the kernel as the container comes up. And then hopefully this will answer your question in terms of like, well, how do you build up a container? Well, a container is actually made out using this union file system. So the union file system basically builds together various layers that are going to sit on top of that kernel. So remembering that the definition of the container is that it has a shared kernel. What else is going on is kind of up to the container itself. So the host might be running one operating system, but the container could be running a different operating system and just sharing the kernel of the underlying host that container is going to run on. And so that's kind of what you've got here. So this is all the stuff we just talked about, the C groups and the namespaces and all that kind of stuff. That's the host layer. That's kind of there and available. And then typically what you'll find is a container will then pick, you can just build straight on top of that. If you just fancy just building straight on top of the kernel, and we see that, you can just say, I'm just going to do that and run my app directly on top of that. But typically you find you want some sort of operating system just to do basic package management, or maybe some of the sort of OS tools that you're not going to get from the kernel. So quite a lot of applications need some sort of operating system. But often it's not necessarily an operating system that you might be using on a host. So you might be deploying your host using, Red Hat Enterprise Linux or CentOS or some of these sort of more enterprise-grade distributions. But for the container itself, you don't necessarily need all of those tools. So you might pick something lighter weight. There are some new operating system out there like Alpine and CoreOS, which are very, very slimmed down operating systems, very, very basic package management, and that's about it. Not a lot of other tools, a lot of other things in it. And that's actually quite useful in terms of like, because you want these containers to come up quickly, you don't want to be waiting for your whole this OS layer to come up. You don't want to be shifting that around. And so getting a very lightweight operating system layer is very useful to sort of build on top of that kernel. And then you might add, some additional libraries, some other things that you need to make that happen, just as you might have done before. And then you have an app layer on top of it. So the app layer then is running on top of all of that kind of stuff. And so, if we're adding Apache, then it might use some of the underlying Ubuntu stuff, but they're mostly using the stuff from the kernel that's there. And one of the interesting things about this is that once I have loaded these base layers in, so like the Ubuntu layer onto a machine, then any other time I get a new Docker container or that I put on that machine, if it's inheriting from that exact same base layer, Ubuntu or whatever, we don't need to pull it down back onto that machine. So as you start a container, it's going to pull all of these layers onto the container, onto the host, build up a union file system. But if it's then starting a second container, it will only pull the differences, the things that are really different between it. So perhaps I'm running Apache, maybe then somewhere else I might be running Nginx, or I might be running Redis or some other technology. But it's all running on top of the same layer system. Then it only needs to grab that stuff once and then build up the container to run. So the union file system is a really useful thing to know about. And so how a container works is all of those things that we've just kind of looked at. You've got your container image, which is built out of that union file system, right? All of those pieces. You've got a network namespace that it's going to run in, so when it starts up, it's going to have its own isolated network namespace, and we'll go into some more detail about how that looks when we're actually trying to getting into the debugging section. And then it gets its own process namespace, its own memory namespace, those control groups, and actually also quite often SE Linux context. So if you're running SE Linux, certainly I would recommend it, particularly in the world of containers, because if you want to make sure that one container really doesn't have access to other things, you can actually lock down. So each container will get its own context, and then if you do really need to share something specifically with the container, you can do that at a very detailed level in terms of the overall security of a container. And so those are the core elements of how a container works and comes together. So I've gone through that fairly quickly, but hopefully you've kind of got an idea. But just let's see if there are any questions on this particular how a container works. Yes, question here. Yes. Mm-hmm. Mm-hmm. Yeah, sort of a pseudo kernel that then maps down to whatever is there and available, and then you then get the other things that are built on top of that. So it's basically this, what is called the boot FS is kind of like the core ingredients. And so if Ubuntu does need something that it hasn't got, is not getting from here, it will bring it in at this layer. Any other questions? I've got a question at the back. Yeah, so the question was, why would I use a container over a virtual machine? So what happens, particularly in the world of microservices, is that because you're tending to break down your application into lots of small individual running processes that might be written in lots of different technologies, they become smaller than the unit of a virtual machine. They tend to become much more lightweight, and so you can kind of carry on. When we did this, we started breaking things into microservices, and we were still using VMs as our deployment unit. And we could do some of the things that containers can do, so you can build up an image and some things. But over time, when you've broken this thing into many different microservices, you find that the virtual machine construct just isn't, it's too coarse a construct. You need something a finer grain so that you can then put multiple services onto an underlying host and pack them together. So that's one big reason why you would go down a containerization route. Is because of that. It's also sometimes in terms, even if you've got something that is going to take over a large amount of a host, an overall host, it's that repeatable file system thing that can give you a lot of benefit, because you know that I can run this anywhere, and it doesn't matter what the underlying host is. So I can be running it on my MacBook and running the container, this exact same container with Couchbase running inside of it. I can take that exact same thing and go and run it into a production environment on a Red Hat or a Fedora or whatever I happen to be running in production. I know that the behavior will be the same right the way through. So that is another, there are plenty of other benefits, but that's probably two of the key ones I would see, is sort of the ability to cut down hosts when you're moving towards microservices, and also just that repeatability. Does that answer the question? Yes, okay, good. Any others on this section? Are you, is this familiar to people? Have people seen this bit before? We've got a few nodding heads, a few people it's new for. Okay. But we all need to know this as we get into the next sections in terms of kind of like working out where we are. So let's look at how to build good containers, right? And so what we find with cloud software products is we get sort of three different things. When people talk to you about, I've got a cloud software, they might have different views of the world. They might have taken something that was running on a hardware appliance and lifted and shifted it into a cloud. And we still see a lot of that going on, right? It's unoptimized. You're really shoehorning it into a cloud environment. And then you've got the sort of cloud-ready virtualized, and this was what a lot of people were looking at, maybe 5 years ago, 4 years ago, before containers were really starting to become an important topic. And so this is sort of a bit better packaged, but it is difficult to break it apart. You can't kind of take a bit of it out and move it about and move it. You've still got quite a large unit. And then your sort of real cloud native is much more like this kind of view where you've got little pieces that you can slip in and take in and take out. You can take the containers in and out. And these are all, you're going to see all of these flavors, or certainly I see all of these flavors of things happening when people have moved to containers. They might have done that sort of first thing and kind of left it in that state and then kind of tried to containerize it. And it's sort of more messy. You might have got someone in this state, or you might have someone started from the point, okay, I'm going to start thinking about what I'm going to build as a microservices architecture. But you're going to find all of these things in containers. And so what I want to sort of talk about here is that what's a really good one, this side, but what else might you see, and what compromises you might get, but how you can guide teams or survival tips to deal with these different things. So let's look at the first of my survival tips. And it's really about just understanding how you're going to build up your containers, right? So there's going to be some code, sort of code examples and command lines in this. So this is the Docker file for a particular microservice. It's my Hello World one. And it's very simple. It's going from a lightweight operating system like Alpine. So it's not really got any real complicated dependencies. It's just got a bunch of Java, Node.js code that's going to run inside of it. It doesn't need to be compiled, doesn't need a package manager, doesn't need any of those things. And so it's starting from something pretty lightweight like Alpine. And so the entry point is a script that's going to run when the container starts. That's what's going to actually execute. And it's going to run, you can see here, it's just running a single command to run Node and that particular script. And this is, an oversimplified version, but this is your sort of ideal. This is that third one on the on the right, where you've got a single foreground process that starts inside of your container based on something pretty lightweight. And the advantages here are that in terms of how containers work, how a container runs, when you start the container, then it will run up a foreground process, which in this case is Hello World. And then when you want to stop that container, it sends the foreground process, PID 0. So in that, if you remember, we have our own isolated namespace. So PID 0 is the foreground process typically. It will send a signal to that first process to say stop. And then it's down to that thing to stop gracefully, stop doing whatever it was doing, right? Stop its processing, if it's a web server, it might drain connections before it finishes. So it's got a chance to shut down nicely, and then it will end. Typically then, the container environment's going to wait a certain amount of time, and then when it reaches that timeout, it's going to send a kill signal, and then it's just going to come down ungracefully. So in a very nicely designed application, you hopefully will see this kind of thing, and this is what you want to be looking for. So if you've got teams that are building containers, or you've got vendors who are providing you with containerization or containerized assets, this is kind of the sort of thing you're going to want to be seeing. But you may see something a little bit more like this. There's nothing totally wrong with this. It's just a bit more of a compromise. So this is probably one of these, either the lift and shift or the sort of cloud ready, something that starts to look a bit more like a VM running in a container. And here you can see we've picked a slightly heavier weight operating system. So if you get a container and the container image itself is quite big, there's a good indication it's probably running a larger operating system. And you can actually use Docker inspect to go and find out what operating system, what the layers are in terms of that union file system of the container. So you can go look at what's going on there. So typically, you know, this is a sign that maybe this isn't in the sort of cloud native world, it's sort of dependent on some packaging things or some, not always the case, but sometimes the case. And this time its entry point script down here is doing something different. It's actually using an old school technique that we used for a long time, sysctl, or one of these kind of process management things, and it starts up my Hello World service in the background. And the problem there is, then it quits, right? So if you use this tool, as soon as that's finished, it exits, and that means the whole container stops, and then the whole thing falls over, because in terms of that process life cycle of a container, once, if process zero stops, the whole container stops. It's all driven off that zero process. And so you have to keep something running in the foreground, something running in PID 0, because all of this stuff is going into the background. And so you end up finding hacky things like this going on, like tail -f/dev/null, or something like this. It's pretty hideous, right? But that's what you might see. I see it in some of our containers that we've got, and I'm trying to get them all that one. But that's what you see something like this. And of course, this is still, if you talk about that life cycle that I talked about earlier, where I'm going to send a kill signal, so I'm going to send a pause and I say, I want you to stop as a container. Well, tail -f is going to stop very quickly. But the problem is there's still all these background processes, and what the container environment, so Docker, is going to do is go, well, I can see there's still background processes going on, so I'm not going to allow this thing to stop. And so then you're in that timeout. And so containers that look like this, they tend to not stop until the timeout, so 30 seconds later or 60 seconds later, or whatever is configured for the container environment. They take a long time, and then they stop abruptly, and then they don't drain down their traffic nicely, and they don't behave very well. And so you can imagine you could write something in your foreground script that's kind of doing a detection of those a sig hup and so on, and then do a sysctl stop on these things. So you can imagine that you can do it. It's just a bit more hacky and a bit more painful. And so, if you're finding containers running weirdly in production environments, maybe they're more of this style, and you really want them of the first style. So the second survival tip here I've got is in terms of building those layers. And this is one that we've used as well, which is really useful in terms of like building a lightweight container layer. Sometimes you actually want your container to do the compilation of your application. It's kind of, in terms of a development lifecycle, it's kind of useful to be able to just say, well, I don't want to have all my compilation environment available because I've got a CI system that's going to build my Docker containers for me. I just want a simple ability to build a Go code on, and I'm not going to install all that stuff. So quite often you'll find people want to just do their compilation inside of their container. So in this case, we've got something that's going from an Alpine image, so it's not bad, but it's from this Golang, and what that's got is then it's going to bring in all of your compilation tools, your GCCs and all of these kind of thing, and it's bulking out that container, which, the bulk is sort of tolerable, but the problem there is you're also about to run this in production, so you're now sending all your compilation tools into a production environment that then somebody could go and compromise. And so you kind of don't want to be in this position. So you can see it's handy, it's useful for the developer, right? The person who's going to Disney World without their kids, right? This is kind of simple. And they expect that to be okay with production. But what you can do, and this is a really nice thing that you can do with Docker, is that you can then start again. So this is still the exact same Docker file, but what it's saying now is I want to start again. I'm going to start from a different base layer, this time an Alpine 3.7, right? And so it doesn't have all those compilation tools. It's not got everything in there. And I'm going to copy from 0, so that's from the 0 to the bottom layer here. I'm going to copy some files. I'm just going to copy the compiled, in this case, Resource Watcher application into this container. And then when I run, I'm going to run that. And this becomes a very, very lightweight container. And so in terms of, again, if you see very bulky containers, you might find that they've got a whole bunch of dev tools that probably shouldn't be there. And you should go, well, why don't you use something like this? This is called the multi-stage build Docker file. And we use this as well quite a lot in our systems to make it easy to compile, but also easy to deliver into production. So another survival tip here is around labeling and tagging. So tagging is basically when you build a container, when you build a container image, you do Docker build, it just spits out some hash number. It's a weird number and it doesn't really mean anything. But what you tend to find people do is then they will tag that with a meaningful name to say, well, this is Alpine, or this is Java, or this is Apache or Nginx. They'll give it a tag, and that tag usually has two parts to it. It will have like a useful name, and then colon, and then the sort of some indicator of the version number. And so what you might find in people's Docker files, if they're wanting to use something they want to inherit from the Alpine image, they might do from Alpine latest. And in development, that's kind of handy, because means I'm always getting the latest version of Alpine down. Every time I rebuild that container, if the latest version of Alpine changes, they just switch that tag in the upstream repos to the very latest thing, and you get the latest container image into yours. But ideally, you want to be more specific. And this is on the right-hand side. And the reason why you want to be more specific is that when you get a day zero bug, those day zero bugs affect the containers as much as they will, so you can go and patch your host operating system, but your containers also have got some sort of operating system in them, and you need to go and identify which ones need to be rebuilt or repatched, right? So you could either, to patch a container, you could either build another layer on top of all of your containers just has the patch in it, or you could make everyone rebuild their containers from a safer base layer. But you need to know this kind of information, and you want to know you're not inadvertently picking up something that is newer than you expected as well. So making sure that you have a tag, and this is for the containers you build or yourselves, or if you've got a service provider, a vendor who's providing you with containers, if they're giving you ones with specific versions, you know what version of that software you're running, rather than just latest. And that we've found is there is a bit of overhead in doing that, because you've got to manage all these tags, but actually doing that gives you a lot more control over what's going on in those containers. And the other thing that you can get in a Docker file is a set of labels. And these are really, really useful things. And I don't see lots of people doing this. I see some people in the open source community doing this. But effectively what it is just giving you metadata about that container. Who made it, when it was made. And this is, so you can, these labels can be whatever random names you want. There is a label schema org that have defined a set of common labels that you can use. And this one is my most useful one, is this VCS URL. It's basically, if I go to that URL, that's where I would find the Docker file and all of the things in it, so I could actually figure out what's going on. And so what's really useful out of these labels is that when you have a container, you can run the docker inspect command against that container image, and it will spit out all this information to you. And so you then can go and find out, okay, what date was this built? Who built it? When did it do? So all of these kind of things. And this data, when you're taking it into a production environment, is really, really valuable to know where these things are, because you can figure out what you're running in your production systems. So this is, I really would recommend. I don't see enough people doing this yet, but getting teams to start to do this really helps. Actually, some of the tools, like, I don't know if any of you are familiar with Artifactory as a tool. You can use it as a Yum repo and a Docker registry and other things. And I think there are probably others that can do this. They actually extract all these labels out. They do a Docker inspect as they load in the Docker container, and then you can go and search on it. So you can do queries saying, give me all the Cisco images from 2018, or from July, or from whatever. So you can kind of do searches on these things, which can be really, really helpful for you managing all these different containers as they go through into a production system. And this is probably the most important one, and it goes back to those C group limits. So when you run a container, you're going to give it those. So you can see there's this minus CPUs and minus memory. That's the C group information. It's telling this container how much memory and how many CPUs it's going to. And you'll see I've deliberately picked some very low amounts of CPU and memory. And inside it, in this particular container, it's running a Java runtime and running something or other, right? And what we typically find is that the gotchas are typically people don't build their applications in a way that are C group aware, i.e. they just assume that, because they can sometimes see the host information, the total number of CPUs, and they make calculations based on that. And so they go, well, I can see 16 cores or whatever it is. So I'm going to start up myself as a web server with 1,000 threads, because I know that 16 cores and 1,000 or whatever. They make calculations that are not aware, but actually all I've been given is 0.1 of a CPU. So if I try to start 1,000 threads inside of my web server, it's just going to fall on the floor. Similarly, from the memory perspective, right? They just don't sort of think about, well, they might have their memory. I mean, in this case, when you're running something like Java, you tend to need to give it a certain amount of memory information. And so making sure all those things line up. I've seen so many containers falling over just because they've not thought about this stuff. It's pretty fundamental stuff to do with containers. But so why is this thing keeps falling over? Well, it's because you haven't thought about the memory part of it. You haven't thought about the CPU part of it. And then it all falls out. So that's an important, probably one of the most important tips. So just to kind of, again, kind of wrap up that section, these are kind of pulling out what I've talked about, that single foreground process in your container that's going to make the life cycle of running and terminating, stopping and starting containers a lot better. So get to those. Try to get some lightweight layers. Maybe use that multi-stage Docker build. Labels and tags, just so you've got all that extra metadata about the container, so you can see its life cycle, see what is going on, and resources and limits. But that's probably my number one survival tip. If people haven't thought about those things, that's typically where things are going to go wrong. Actually, the labels might seem like a trivial point, but actually just having one label that tells you where is the Git repo, where this Docker file is actually my second most important thing out of all of this, because when you've got that, I can go back and really look at how a container has been built and understand where it is, what is the source of it. So that would be my tip. So that's my sort of survival guide on the sort of how to build good containers. So before we get on to debugging containers, which will be quite fun, is there any questions on this section? One question here, yeah? Okay, two questions. Great. So the question is, is that your first question? Yeah. So the first question is, just for everyone else in case you didn't hear it, how can you, CPUs how do you allocate a percentage of a CPU? That's not how CPU, and it's really just time slicing. It's how many time slices are you going to get of that overall CPU in time. That's kind of how it's doing it in a mechanism. There are a couple of other things that you can do to say, I actually really want dedicated that whole core or that whole CPU. You can do some of those more sophisticated things, but typically it's a time slice. Okay, and the second question? Mm-hmm. That was that the multi-stage one? Let's go back to it. This guy. Yeah, so this is just the build time. So this is just at build time. So once I'm finished, all I end up with is these layers. And this stuff has been completely thrown away by the build process. So actually, if I were to do a Docker build on this file, what you would see is it does all this kind of stuff, and then it gets to this point, and it junks. Well, it doesn't junk it. It keeps the union file system around temporarily that it built, because remember there's that union file. It keeps that around, and then when it's doing this copy, it's ripping it out of that other union file system, copying it into this new union file system that it's building, and then done, and then it throws all of that away. And so you only end up with this piece here. Yes, yeah, this is just a build time. Yeah, and then you're running this bit. This is the bit that's actually going to be run when it runs. Well, actually, that's running, right? So it's not actually running this copy command when you run. When the container starts, it's just the command, right? That's the foreground. Is that okay? That answered it? Another question? Yes. Yeah, so the question is, sometimes you'll find on the end of each of these lines an ampersand, and then it sort of goes over multiple lines, and you'll get the slash as well, backslashes and stuff like that. Yeah, so if you want to do running multiple times a build time, so you want to make a directory, copy some files into that directory, untar something, do some other things as you're building the container, everything that's in one line, which will have those continuations, is a layer. And so the reason why people do that is because they don't want to have lots and lots and lots of layers. They want to keep it as just one simple replaceable layer. And what that means is that, when they subsequently rebuild the container, if your system already has a union file system with all of those commands already executed, it will just skip over that and just do the bits that have changed after it. Does that answer the questions? Okay. Any other questions on that section? No, great. Well, thanks for those questions. Oh, we did have a question. I'm not so familiar with the world of Windows and containers. It's mostly something that you'll find. But I guess perhaps because Windows is now starting to build in sort of Linux-y type kernels into new ones, then perhaps that's available. I'm just not familiar with it, so. Okay, let's go on to the next section then, which is going to be debugging a container. And this is really, like if you actually end up operating, if you're not building these things, so getting it right in the first place and building them good is great. And even if you're not, you can be a champion for a good container. You're going to be faced with containers running, and you're going to have to debug them. And you kind of get into this kind of strange situation. So, so when you're running a container, so someone started a container up on a host operating system. And that could have been through Kubernetes, or they could have just done a Docker run, or they could have used Swarm, or they could have used all sorts of different ways in which they got that. But you can basically do this Docker PS, and it will give you a list of all the containers that are running on that particular host. And so here I've got a container with a weird ID. And I'm going to go and execute into that container /bin/sh. What this command, this command kind of fools you into thinking that you're SSHing into a virtual machine. It really feels like that, because the -IT means go into interactive mode. So normally if you didn't do that, it would just execute the command on the end and then quit. So you might do it just to do cat of something in the file system. But when you do this, it feels like you've SSH'd into a virtual machine. You're not really. You're executing a command in a running isolated PID namespace, right? That is those C groups and those namespaces, all those things that we talked about at the beginning. That's what you're really doing, but it kind of feels now like we're in a virtual machine. And so let's try some of our favorite commands. Okay, why is PS3 not here? TCP dump, I need that. Where's it gone? Oh my God, I can't even do wget. Right, I mean, it's like you're suddenly, wait, this is crazy. I know these things are around. In fact, I know the operating system of the host has got all these things, but why aren't they in my container? This is crazy. And how am I going to debug this thing? How am I going to do this? Because I need these tools. Well, I mean, of course, I could have those tools, but I've started from a base Alpine image, which doesn't necessarily have all these things in it. So this is Prometheus, which is, we'll talk a bit about Prometheus towards the end of the talk. But this is an open source container image, and it hasn't built all these tools in because it didn't want to bloat the container image with all those things, all those tools. So they're not there. I could go back to the developers and ask them to put these tools in, but do I really want to be doing that? Going back to all of the people? It just is, it's not going to work. So we've got to find a solution to this problem. How am I going to debug my container if when I looks like I'm SSHing in, I'm not really, I'm just kind of executing a command in it. I haven't got any of my tools that I'd be used to using. So let's do another survival tip. Let's just use one of those, the PS tree. How do we get a process tree out? So going back, we do the Docker PS. We've got a container ID, and I can run this docker inspect command, which I've been talking about a little bit before in terms of it's able to go in and look at what's going on in a container. And so what I've got here, docker inspect, is looking for this kind of weird, I don't know what this really means, this curly braces thing. But basically, what it's actually trying to do is give me the host PID of PID 0. So inside the container, this would be PID 0, right? And this will be the started process inside of it. But actually from the net, that's in its own namespace, its own PID namespace. In the real namespace of the host, it's on PID 12407, and so now I can just run PS3 against that normal thing, and I can see what's going on inside of my container, and I can see the full trees. That you can see there was some shell script that started Prometheus, which then forked a bunch of processes off. So this is actually a good looking, if you're talking about like a container that's got a good, is well made and it's got a single foreground process and stuff, this one looks quite good, right? Because it's got a script that started a foreground process and then it's got its set of forked processes inside of it. So this is a really useful tip. By the way, all this is in your PDF, so just don't worry about writing them all down. But this is really an important way of, okay, now I can at least kind of figure out, well, I've got something going wrong in my container. What's going wrong? What are the processes? This is going to give me kind of the idea of what's going on. So the next one I want to talk about is my TCP dump problem, right? How do I deal with that issue when I haven't got TCP dump, but I need to figure out what I've got, So in the video space, we're always using TCP dump all the time because we're seeing massive chunks of video going around the place, and we're figuring out why we're not seeing packets arriving and so on. To do that, I'm going to have to go and explain to you a little bit more about the container networking. We talked a little bit about namespacing. And let's have a look at really what happens when we start up a container. So I've got my root network namespace. It's maybe got an interface, ETH0. It's got an IP address attached to that namespace, into that namespace. So that's what's on the host operating system. It might be a VM, or it could be a piece of bare metal or whatever. So that's kind of what's really going on in the real world. And what happens is, so I start up my container. I'm going to run a Redis container. So Redis is a caching layer. I'm going to run that on this host, and it creates a namespace for it, and it's going to create an interface, ETH0, and it's going to give it an IP address. It's not going to be in the IP range of the host, but it's going to be some IP address, right, that it's got. So that this thing, when this thing runs, it can just think like it's running on a virtual machine. It's got access to an IP address and so on. But that's not in the real world. This is sort of a fake IP address that doesn't really exist. It only exists in this namespace. So how do we get this thing to kind of talk with the rest of the world? Well, what happens is that ETH0 gets mapped to a virtual interface. In this case, I've got VETH1, right? So you've got a virtual interface that is one-to-one linked to this, right? That's an important link. And what happens then is, if I've got another container on here, so let's say I'm running Nginx, which is a web server. I want my Nginx there running. It gets its own IP address, its own ETH0, but that's really linked to VETH2. Right? So we've got two virtual interfaces which are linking internally into what seems to be the same interface, but it's all within those namespaces. So this is kind of okay. We're getting there. We still can't get my Nginx to talk to my Redis container because they don't know about each other. And so we bring in a bridge interface. And typically, if it's just running Docker on its own, it's often named CBR0, but you'll get different names depending on specifically the runtimes. And actually, the commands to run all these things are at the top there. So you can see we created the bridge network, and then we ran these two containers linked together with that bridge network. And when we get to Kubernetes, I'll explain a little bit more. It kind of automates all of that for you. So this is starting to look good. It means that now Nginx, when it wants to talk to Redis, it can just talk to 172.19.02 and it works. It goes across the bridge. But what happens when I want to access my Nginx container from the outside? I want to access my web server from the outside world. Well, the outside world can only see 10.1.50.0, so we need something to get it down into this one. And we've got all the ingredients in the right place in the root namespace. We've got a little bit of a problem with these IP addresses. And so the solution to that is our friend IP tables. And so what IP tables will do is it will do a NAT translation of that. So basically, if I'm accessing port 80 on this particular host, it's going to then come through, it's go, okay, I know that that actually really is the Nginx down here, so it's going to then NAT that, translate it into the 172, and then as the packet goes backwards, it's going to reverse that NAT back out again. So that's kind of like what's going on in container networking, and this is a really important slide. Until I understood, came to understand this slide, I really didn't know what the hell was going on. I could see that containers were getting all these IP addresses, but didn't really know. And I'm not a networking expert by any stretch of the imagination. I'm a video and applications guy, but until I kind of understood this, I didn't really know what was going on. But this is going to give us a good clue as to how we can go about doing my TCP dump. Has anyone got a clue how they're going to do it? Always looked in the next slide. Let's see. So back to, so I've got my running container. So this was the from that Docker PS. I just stopped putting it on all the slides. What I want to do is I'm going to run this another command. So again, Docker exec. But this said, remember that original one when I had -it and /bin sh, that put it interactive. This is just going to run that command and quit. And what it's doing is it's looking out for that ETH0 that's running inside of the Docker container, so it's ETH0. What is that linked to? What's the IF link to it? That's number 12 in this particular case. And if I then go and have a look for all my VEIF, my virtual interfaces, I can see that number 12 relates to this one in purple that's 8004 and all the rest of it. So that's actually the virtual interface that is relating to this container. So if I actually want to TCP dump what's going in and out of the container's ETH0, I actually care about my virtual interface, and so there we go. TCP dump, point at that interface, and hooray, I can now figure out what's going on. In this case, it's Prometheus, so it's doing a whole bunch of kind of stuff talking. And I did this in a Kubernetes cluster, but you could be doing this on any other of your favorite ways of running a container. And this is a really useful tip, and obviously you can then, knowing this, you could actually hook your TCP dump at some of those other interfaces, the bridge interface as well. It can be often a useful thing if you want to see what's going on, the traffic that's going on between two containers that are on the same host. You can go and hook yourself into that point, so you can kind of choose where you want to do. And because I'm, typically when we deploy containers into our solution, we run CentOS as our base operating system. I can make sure that I've got that tool available on the base OS, and I'm still able to go and do my TCP dump. I've just got to kind of figure out a little bit of stuff on top of this, and I can imagine that someone would write a script to do this, this kind of thing. So they just simply, script up all that, what I just did, to look up the virtual interface and start the TCP dumping it. So the tools are there. There's just a kind of a different way of doing it. But it's important to know that, and I certainly have found that when we've been trying to put our containers into production, our operations teams, who are familiar with the usual operating, the virtual machine or base operating system tools, they're like, I don't know how to do anything. You've taken all my tools and all this kind of stuff away. And so your blocking point comes, well, there's just a lack of knowledge in my operations teams to how they're actually going to do their day-to-day job of working out when things are not working properly, right? Again, this is the Disney World with kids problem, right? You've just got to deal with it. So I've got a question. Go on.
So you're talking about going from Docker basically. You're kind of from the base platform, going, patching the points inside the containers. How much awareness do containers have the other way? So they have to know where they are hiding on the network and things like that. How much can they know honestly about where they're running?
So the question was, how much does the container know about the rest of its environment, the things it's running? It doesn't know about any of that stuff that I just showed, the network namespaces. It feels like, again, it itself is a virtual machine or something, It doesn't know about the bridges or any of that stuff, and it can't assume any of those things are going on. To it just feels like there's a nice, happy world where there's just IP addresses and it can go and contact them, and it really doesn't. Yeah, so if it's syslogging, then it's syslogging actually inside of the container. It's not actually going to the host syslog at that point. And so, yes.
Whatever you're doing.
Yep.
All the remote logging.
Yep. How does it know?
Well, like if you're looking at the logs, you say, well, where's that container? Like, how do I find that instance?
that particular, how do I find, how if I'm looking at where is that container, okay, we'll get onto that on Kubernetes, right? Or Kubernetes is a way of doing it. There are other things, but when we talk about Kubernetes, that's the missing link that you don't have, is like, at the moment, if I've got some IP address in some random range and that's appearing in my log files, right, I'm seeing back on this page, I'm seeing this IP address, where is that IP address? How do I find it in my big network? You need something like Kubernetes or an orchestration tool to help you resolve where that IP is. If you're just running individual hosts and doing this stuff, this becomes really hard.
The outside world is seeing 10.1.5. The application, to your point about your normal tools, I normally know where this host is in some way.
Right.
And trying to basically solve that problem.
How do I get back to where that container is or where it is? And right. Well, let's see if we can find that answer in the Kubernetes section. And if not, we'll address it maybe afterwards or a bit more detail. But you really do find that eventually you need an orchestration system and some other networking tricks to kind of figure out where everything ends up when you've got containers. So we'll look at that, and we'll also see the metrics and monitoring stuff as well towards the end. There's some tips in there. So let's see if we catch those. If not, we'll have a chat. So these were the kind of survival tips for this section that I've got in terms of debugging containers. So you can still keep those debugging tools on the host OS. I'll take your question just one second. Debugging tools on the host OS, but you might not find them inside of the container. So know how to query, these C group and namespace things. But remember that Docker exec is not the same as SSH. I sort of said that before. But it fools you into thinking it, but it really isn't. It's not the same. You are executing a command in another namespace that's still on the same host or so on. But that's a kind of, hopefully you've seen some good survival tips. I had a question. So the question was, do containers always have to use NAT to get to the outside world? No, they don't. So typically you will see that because you're going to want to have multiple IPs, virtual IPs of each of the containers. You can run a container in host networking mode, in which case you don't have all that virtual ETH and all that kind of stuff going on. It's just the container actually sees the real interfaces, and it will see all of the interfaces of the host. If the host's got many interfaces, it just sees all of those, and then its IP address becomes the host IP address. So it is possible to run in that, and it's not advised. And I've got a little bit towards the end that talk about it in the terms of ingress and egress reasons, in terms of when you're running a large cluster like Kubernetes that you might run in that host networking mode. But generally, often the reason you end up in host networking mode is because you can't tolerate the NAT, right? But there are different. We'll get when we get into Kubernetes section. There are some other tools and other things that are going on. Oh, sorry. Did that answer your question? Okay.
I just wanted to add to the NAT thing. In our experience, using the load balancer with the NAT only, like it does, is kind of a pain in the ass. Because it's like double or triple translations. So we actually disabled it, and we actually we have 5 bit pretty much. So we ended up using some other tool that is, what's the name of it? It's made by the same tool, and it's made by Google too. But it does the translations for you, like at different levels to the OS level.
Okay. Well, if you do recall it, can you put it into the chat room afterwards, just so that we can connect? It's good to share that some of this. I'm not familiar with that particular tool, but yeah, please do. If you wouldn't mind, that would be great to chat that into the room later. Any other questions on this debugging section before we get on to the next bit, which is Kubernetes? So there are a range of different container runtime environments out there that can basically deal with a situation where you don't just want to run a single container or a few containers on a single host. You have huge numbers of hosts, and you want to manage the running of those containers on all of those hosts. There are various options out there. Kubernetes is pretty much the one that most people are turning to now. It's becoming the de facto standard. You're finding that most of the cloud providers are providing Kubernetes services. So Google Cloud have had it for a very long time. Amazon have now just launched EKS as a service as well, so they've got it. Azure also has it as well. So a lot of the cloud providers are getting behind Kubernetes as a project. It's got a massive open source community, lots of people doing it. So it's the one, I tend to pick technologies that I can find lots and lots and lots of answers for, through Google by just get this thing, Kubernetes, this thing, and you'll find a lot of answers. So it is kind of becoming the de facto standard. There are a few others, but I'm going to talk mostly about this. It's what we're using for all of our applications, Kubernetes. And of course, the Cisco container platform is built with Kubernetes. So let's just go through some high-level constructs in terms of, how Kubernetes works. If you've, how many people are familiar with Kubernetes in the audience? With a show of hands, a reasonable number. Hopefully. So this is just a very quick bit of a revision for the next bit. So the first concept that Kubernetes brings in above and beyond underlying containers is this pod concept. So the pod allows two containers to reside on the same host. It basically guarantees that both those containers will run on the same host. They will get a shared IP address. So the IP address is then at the pod level. And then you can choose to bridge the namespaces between the two. So you might want to say, well, I want to be able to share the file system or some part of the file system between the two containers. So the two containers still got their isolation, but we're specifically choosing, because they've landed on the same host, we now can do that. If they had ended up on two different hosts, I couldn't share the file system because it would be a local file system. So typically an example of where we use this is we'll have a main container. Let's go back to the kind of Nginx example. We might have Nginx or Apache or something as a web server, but we need some sort of log forwarder for it, or we need some sort of plug-in to it, or something that's running as an additional process that's very much wanting to go in and grab information library, through a socket or through the file system, and then maybe forward logs to something or so on. You'll often see that kind of pattern. It's called a sidecar pattern, where you've got like the main thing and then some helpers. So this is a useful construct. You don't have to use multiple containers in it. Often a confusion that some people do is they end up saying, I've got a whole bunch of microservices, I'm going to put them all in one pod, and that's kind of broken the idea. The idea is just only if they really need them to be running on the same host, then you'll put them in. And it's typically this sidecar pattern. So that's what a pod is. It's sort of allowing two containers to share some of the things that you wouldn't normally be sharing between containers. They still have their own union file system and all that kind of stuff. And then you have this concept of a replica set. So a replica set allows you to run, say I need multiple of this particular pod, so I need 12 of these running, and they'll get scheduled across the different nodes in your cluster. A replica set is usually created using an object called a deployment object. There are some other types of sets now in the later versions of Kubernetes, a stateful set, and then there's a daemon set and others. Basically, there's still sort of a set of pods of some form with slightly different characteristics. And then if you've got a bunch of pods that all belong to the same replica set, you might want to configure them in the same way, give them some of the same information. And so they have this concept of a config map, and that config map is an object that gets stored inside of Kubernetes. It's available through its API. It's actually stored in etcd, which is what Kubernetes uses as its backing store, but it is only really accessible through the Kubernetes API. But each of these pods can then mount that config map as a file system onto the file system, or it can use it for its environment variables or for the command line arguments that it's going to run. So it can get a consistent runtime for that particular container. And so sometimes you find the reasons why some people need to, if they've not got a particularly C group aware container, they might need to provide it with a memory parameter. They might put that in the config map and have it match the C group limits that the pod gets given. Sorry, the container in the pod gets given. And then there's an additional construct. So if you've got a bunch of these pods and you want to access them, well, each of these pods gets its own unique IP address, but the IP address is going to be sort of ephemeral. It's going to kind of come and go as you scale up or scale down, or you replace pods. So typically you often want something, some sort of construct to balance the load across them. And this is where the service construct comes in. It's giving you a virtual IP address within the cluster that you can address and say, I just want to get to all of the Nginx in this cluster, or I want to get to all the Redis instances or something, and it will provide then a round robin round the pods. It's not a sophisticated load balancer, but it's generally typically good enough to get you what you need. So these are the kind of like the core constructs that you're dealing with in Kubernetes. There are loads more, but these are like the real fundamental ones, and the ones that I'm going to talk about in terms of some survival tips. So the first Kubernetes survival tips are these guys: liveness and readiness probes. So each pod can have this specified in it to say, in fact, it's each container in each pod can have these things specified to tell the outside world how it's getting on, right? Whether it's alive or not, and whether it's ready to receive traffic. And so the liveness probe, what happens with the liveness probe is typically just like a ping. Sometimes it's just a process check. So whilst I've got some examples here that are, querying an HTTP GET against the web server that's running on that port, the HTTP port inside the container, sometimes it might just be a process check. It's just PS minus EF grep for this thing, or something very, very basic. But it's basically is this thing alive at all? And what Kubernetes does is that if it's not alive, then it just kills that whole pod and then starts it back up again. So it's kind of providing you that sort of restart mechanism of the containers. And this comes back to those earliest survival tips around the, having that single foreground process. This is the thing that's actually doing the restarts for you. So you really don't need a thing inside the container doing restarts. This is the thing that's going to do it, and it will deal with it. If there's some problem on the host, it might move it to another host, or it might restart it on the same host. But Kubernetes is providing that level of control, and liveness probes can be really helpful for that. It can actually help with that example that I had in terms of if you've got multiple background processes in a sort of lift and shifted type of container, you can actually say I'm alive if all my background processes that I know about are up, and if they're not, then kill me. So you can kind of deal a little bit with the kind of not so pretty well with the liveness. The readiness is basically am I ready to receive traffic? Can you start sending me? So my web server might be up, but it's still warming up caches, or it hasn't done something, or it's a whatever it is, RabbitMQ for a messaging queue. It's ready and up. Maybe it's joined a cluster of other things that it needed to talk to. The readiness probe is specifying some call that the Kubernetes environment can call to say, are you ready to receive traffic? Are you ready to get things? And these are really, really important. And if you are seeing, when you see a Kubernetes YAML file or JSON file that specifies the whole definition of a pod and the containers and all these kind of things, go and have a look for these things and see if they're there. And if they're not there, go and ask why the hell they're not there, because without them, you're sort of a bit blind to know whether something is okay. And there's a few exceptions to the rule, but I would sort of kind of generally start with a position like, why haven't you got these things in place? Because if you don't have these things, how is Kubernetes going to really know if you're ready to receive traffic or manage you as a container? So let's have another extension of the networking discussion, just very briefly, just because I need to introduce a couple of other things. So this is what we saw earlier in terms of like a single host. You've got your bridge network and all the virtual. This is basically the same picture I had earlier. So the first thing is, well, how do we achieve that service layer? Right, how do I have that virtual IP that is going to be available for all the pods that are running on it? So I want to have one single IP address. Well, I just put some more stuff in IP tables. so IP tables is going to be a world you're going to live in when you start using containers, and even more so inside of it. And we'll look at the details of that in a minute, because it's quite an important one to look at, the way in which that gets played out. So that gives me an ability on every host to kind of have this random, this fixed IP address that is going to then maybe send traffic down to containers on that. And then you've then got another host, right? And that host has got its own little world to deal with. And one of the first core things that you'll do is, because you want each of the IP addresses in of all of the pods to be unique, one very simple way in which Kubernetes deals with it is it basically just gives a CIDR range to each host and says you can just use this CIDR range to allocate IP addresses as you're bringing up your containers. And so you can see these are in the 1031s and those are the 10129. And choosing that, which is a setting you'll get in Kubernetes as to how big one, basically determines how many containers you can run on a particular host. Because you'll run out of IPs if you don't pick a big enough one, but obviously pick a very big one, then you're going to need a very large IP range. But these IP addresses are typically not in your host range, your real networking. They're typically done because you're going to have so many IPs, and you have so much of this floating around, you typically end up running some sort of overlay network. And so there are different options out there that Kubernetes can run with. Quite a lot of them use something like a VXLAN to allow these things to talk to each other. So for this container here to talk to the Redis over there, it's still going to want to use that same IP. So they all think that they've got these IP addresses, and this guy can talk to this guy through that principle that the IP addresses are not doing any NAT translation within Kubernetes, but instead what happens is it hits the bridge, and then it gets encapsulated using the VXLAN across, de-encapsulated, and then directed over here. And so this it makes it feel like, again, these are virtual machines that have each got their own unique IP address on them, but actually there's a little bit of trickery going on with an overlay network. There are some ways in which you can run this with an underlay network. So these could be real IPs that your router is dishing out. And again, back to the Contiv plugin, it can run in that mode. It can run in overlay or underlay. And there's kind of trade-offs as to which one you pick. But typically, you'll find the majority of places are using some sort of overlay network to achieve all this. Just going to take a quick pause because it's quite a detailed slide and see if there's any questions on that. Okay, so in terms of like bringing those things together, when I've got my two pods, I've got two pods that have started up in my network, my Kubernetes somewhere, and I want to address them. So I've got a service, and the way in which my service relates to these pods is based on a selector. So you can see the selector is looking for pods which have a label called app equals my app, and you can see these guys are both labeled with that. So both of these pods are a candidate to direct to under that virtual IP of 10.10.10.1, right? So if I hit that IP, these are two candidates that I could send traffic to. But there's another object that gets created so these are objects that you will have created, or your orchestration scripts will have created these things. There's another one that automatically comes along, which is called an endpoints object. And this is probably one that people may not be familiar with, but it's a really useful one. And we spent a lot of time debugging containers and what on earth was going on, and ended up learning a lot more about this endpoints object. So this automatically gets created by Kubernetes. You can query it through the Kubernetes tooling, and so you can do kubectl, which is the command line tool, get endpoints, and you will see endpoints. And you see the name of the endpoint actually matches the name of the service. But what it's doing is it's providing you a single object that then gives you a list of IP addresses that you can actually go and talk to for that particular service. And in this case, there aren't any. And the reason there aren't any IP addresses in this particular object at this point in time is that neither of my pods are in a ready state. So going back to that readiness probe, neither of them are ready. But as soon as one of them becomes ready, so the pod 1 is ready, you can see it copies across and puts the IP address into the list of IPs that are now valid for my service. And then I do it again. This one becomes ready and it gets added. And obviously if they go into an unready state, so let's say the service is overwhelmed, this pod is overwhelmed with traffic, it might go into a non-ready state, and then it will then being able to stop sending traffic. Now, an important thing to know is that all of these objects inside of the Kubernetes world are available through the API, and they are also, you can get notifications when they change. So you can listen for events on change. So if I wanted to implement something that understood when things were changing in a particular endpoint, I could actually watch that through the API, and it would automatically give me notifications when the 120, the 10.1.2.3 got added, and then the 1.4.5. As those things got added, I could be notified to that change. And that is exactly how Kubernetes then implements the IP tables rules. It runs a thing called the kube proxy, which is kind of a funky, weird name. It's not a great name for what it does. It's not, when you hear proxy, you kind of think of something typically in user space, and it can run in user space. You can pass your traffic through it, and it acts like a reverse proxy, but nobody really runs it in that mode because it's not very scalable. Typically, and most Kubernetes clusters are going to run it alongside the IP tables that I mentioned before. And so what it's doing is it's listening for these changes. So it's looking for services. It's picking out that IP address, the 10.10.2, and it's listening for changes to the associated endpoints, and it's writing those into IP tables. So you basically have something that's in the IP tables that says, on this host, if anybody tries to access it, these are the 2 IP addresses I need to do. And this kube proxy is running on every single node in the cluster. Right, so every node in the cluster is doing the same thing, slightly asynchronously, because they're all listening to changes to the Kubernetes API. But eventually, in the sort of eventual consistency world, all of them will end up with an IP table that looks like this. But understanding this piece, the reason why I put this up here is because we had issues when we were running it where the kube proxy was not keeping up with changes quick enough. And what that meant is we were getting inconsistent results. So we were trying to access 10.10.1, and on some nodes it worked, and other nodes it didn't work. And we were like, well, what's going on? It was because of this whole process. This whole process was not keeping track. Now, this was on pretty old Kubernetes versions. It's all been kind of fixed in the more current ones. This was a 1.4 Kubernetes, and we're now on 1.10. So quite a few years ago in terms of age. But this was a sort of a world that we lived with. So understanding that what's happening on every host in the cluster is having these IP tables updated, and they're dealing with that by listening to the Kubernetes API for these different objects. It's a really important kind of construct to understand. There is actually versions now of the kube proxy in the later versions of Kubernetes that can do this with IPVS instead of IP tables. So there are newer techniques available, but the predominant one, the default one that you're going to find is going to be IP tables, not user mode and not IPVS. But I guess over time we might see IPVS taking more of a role rather than IP tables. And there's swings and roundabouts about that. But let's stick with the IP tables, and we're going to kind of debug what's going on with this. So we're looking for a service in the IP tables. The IP tables save, I'm looking for the kube services. So these are all the services, all those virtual IP addresses. And when I get through there, I can sort of scan through this, and eventually I can find Prometheus, which is the one I'm looking for, and it's this one in red. So this is the entry in IP tables that I'm going to go looking for, the one in red. And what that says when I go looking for that is this is giving me a random statistical mode, random, with a probability of 0.5. So I've got 2 pods behind it to go to this thing over here, this green one. And when I go looking for that guy, then you can see these are the actual pod IPs coming to play. The 10.30.0.1, that's the actual pod IP that I'm going to go to, or one of them. Then there'll be another similar rule in there as well that I can go look at. So getting familiar and going, I mean, when you first look at these IP table rules, it's kind of crazy to figure out what on earth is going on. But getting some familiarity and understanding of this is going to be really important as a survival tip, to understand that these IP table rules, they're very difficult to understand. And when they work, you don't care about them. But when they don't work, you really do care about them. So get a bit familiar, play with these kind of this and get familiar. The last one I wanted to talk about in terms of Kubernetes, and there's plenty more that we could talk about. This one I think was useful, was picking the right type of way of getting traffic into your cluster. So there are actually a few different options that are available. The first one that you find typically is, so I've got a VM over here. I want it to talk to this pod in here, running on this node, but I don't have access to it because it's in its own little IP range that I have no access to from the outside world. So the first option that you have is where we've been talking about a service with a cluster IP, so that's a virtual IP that's available inside of the cluster. I can actually run it in a mode called node port. And what that does is, by default, it will randomly allocate some port in the high ranges, the 30,000 range, on every node in your cluster. So that's why it's called node port. It's every node in the cluster exposes that port, and then I can punt my traffic into that port from the outside world, and then what happens is the IP table rule on eRUI, so this one's going to go, well, I don't have any pods, but I do know about these ones, and it's going to hit that very same IP table rule and punt the traffic across and up to this node here, obviously going over the VXLAN encapsulation, all that kind of stuff that we looked at. So that's your kind of first one, and typically when you see this being used, you'll find this being used with a load balancer in the front end of it. So you actually can do service type load balancer, which creates a node port in the random range, and then it adds it as a back end to another load balancer, which might then expose port 80 or something else. So this is how, if you get some of the native integrations with AWS or Google or some of these other ones, you might actually have an automation of a load balancer as well. But sometimes you don't have that, and you pin the port number and you just configure an external load balancer to do that. The second option is host port, and this is where people often get very confused between the two of them because they sound so similar, host port and node port. So host port, basically, instead of doing all this stuff, it takes the pod itself and exposes the internal of this port to the outside world. So it really runs on port 80, but only on that one host. So it's not going to spin up port 80 across the whole cluster. It's just on this specific host where this pod is running. And typically, you'll see this being used in scenarios where you don't want to be having this IP tables fiddling about. You're still going to go through a DNAT here because it's still got to deal with the fact that it's coming into this 10.1.2.11 and that pod is running in the pod IP range. So you've still got that, but if you don't want to tolerate this is sort of a model. And again, you can do the same thing with the load balancer out the front of that and track it. The only challenge there is it's going to be, as these things move around, they're going to move around a lot more frequently, whereas the service, because it's on every host, you can just, a great way of doing the load balancer is just, say, well, I'm going to point my load balancer at all the hosts in the cluster and then just do a health check to see if the node falls down. Here it's a little bit more tricky, but it is a viable option. And typically you'll see it with the next kind of world, which is ingress. So what ingress does is it actually puts the load balancer into the cluster. It actually runs some sort of, typically an L7 load balancer like HA proxy or Nginx, something that can run as a reverse proxy. It puts that into the cluster, running it on a host port, right? So it's going to expose it to the outside world. And then what it allows you to do is do some path matching. So this can now work as a virtual hosting, so I can basically give it, I can point my DNS at this particular port or multiple of them, and then it can say when it's / this path, it goes to these containers. When it's some other path, it goes to other containers. So it can do a full virtual hosting based on that L7. And this is what we use for a lot of our traffic. This actually is seems to be a much simpler model for us to do. We still have to make it highly available, but it gives us a lot more flexibility than having to open all these kind of random ports all over the place. We've still got basically, if you want to come and access services, you go through this port number. Obviously, if you get to huge scale, you're going to have to scale up this load balancer in some way. And so we don't use that for video traffic, because when we've got video segments, MPEG segments and all these things, it gets too big, and we use the node port. So this is your third option, and your fourth main option is what I mentioned earlier about host network mode. So you can actually specifically tell this pod that I need to run in host network mode, which means that its IP address is this IP. It actually then, it's quite an elevated position because it's now seeing all the interfaces of that host, which might have many. It's got a lot more visibility of the networking stack, but this is the only way you can do kind of funky things like if you need to do a multicast join, which is something we often need to do in the video world, as we need to do a multicast join to a source video that we're going to then transcode and make available and package and deliver to the outside world. We don't do this with our playout part, the origins and other things. They can just run through one of the other techniques. But if we've got an encoder and it needs to join something multicast, or you've got something else that can't tolerate that NAT translation. You can do this, but this is the one that you're starting to move further and further away from some of that benefit you're getting from Kubernetes in terms of its ability to isolate the networking and so on. So that's deploying using Kubernetes. So, you know, my survival guide here is use those liveness and readiness probes, understand that endpoints and services. I wrote a blog post also about this. So if you look up stephentalamy.wordpress.com, there's a blog post that talks a bit more about this as well. I'll put it into the room after this. And also, you know, if you're not familiar with IP tables, you're going to have to be if you're going to start to have Kubernetes clusters running. And think about those ingresses and their trade-offs to each of those options. So any questions on the Kubernetes section? Okay, so we're into the home straight now. The final topic, monitoring containers in production. So if you've been doing monitoring, typically it will be quite host-oriented. So we've been using Sensu as our monitoring tool for quite a while, as we've had virtual machines. But obviously there's lots of others. But they're very host-oriented monitoring techniques. So some of the things that you can't see here, well, unless you've got really good eyesight, the sort of things you can see here are things that are checking the disk and the load of the underlying host, which is kind of useful, but not very useful if you ran those checks inside of a container where it's a C group and it's all that other stuff going on. It's not really a useful check to run inside of a container. You still need it on the host because you need to know when your host runs out of disk or is resource constrained, but running those kind of checks inside of a container don't really make sense. Then you tend to have these, you know, these are check proxies, like is this process, if this process is running on this virtual machine, I know this virtual machine is good. This is my HA proxy virtual machine or my Elasticsearch virtual machine or my something else, right? To know that this thing is good and providing a service, I can check that this particular process is running on this host. I can't do that now I've got containers because I don't know whether that container, you know, all of the hosts are kind of general purpose now, and so my containers could be running anywhere. So they kind of don't make a lot of sense to have these kind of checks anymore. And really, those get replaced by the liveness and readiness probes that Kubernetes is providing. So that kind of stuff isn't really very, very valid anymore. But these were some of my initial kind of main checks that I had to go and look to see, you know, was my application healthy in a general way. And then I might have some other kind of ones that are going in. This one's looking at quotas and stuff. So it's going and checking against a Couchbase instance to see if we've run out of stuff. So you've kind of got some checks going on. But really, those things are looking at metrics from a particular thing. So as you move towards containers, you kind of start to feel that you need to move away from this host-oriented monitoring. And so whilst we still use UR to a certain extent for some of our checks, we are moving away from it because we need something that's more application-centric monitoring. And the predominant one, and this is the one that the Cloud Native Foundation is kind of backing, is Prometheus. How many people here have heard of Prometheus? A decent number. Some people new to it. So it's this is really, it takes monitoring a slightly different. At the core, what it's doing is I'm going to monitor my system using metrics. That's the core. So what it does, so if you've had metrics solutions before, you might have used something like an Influx or one of these kind of things. They've typically posted metrics to some server or some time series database that's then saved those things, but it hasn't typically been used for their monitoring purposes. It's been more for historical analysis or these kind of things. What Prometheus does, slightly different, is that it basically pulls the metrics from the source. So it goes out and it queries the API of the application or of the host or whatever and queries it on a polling basis. So every 10 seconds it goes out, it queries and pulls the metrics in. And it does that using service discovery typically. So it will, if you're running it with Kubernetes, it can automatically discover all of the nodes in your cluster. It can then query all of those nodes and find out their CPU and RAM and all those kind of things, some of those basic metrics that we were seeing with checks before. And it can then go and look at every container and look at all the C group usage, so you can see the memory allocation, how much has that container requested, how much is it using, so it can actually go and inspect all the containers through service discovery. And then if your application has metrics exposed with the Prometheus API, which is a HTTP API, you just hit /metrics typically on it, and it has a specific output format with a whole bunch of numbers that particular application can do. So in this case, my Couchbase example before, there is an exporter which can run alongside normal Couchbase that can export the metrics out of it in the Prometheus format. So there are quite a lot of applications and a lot of environments that are starting to natively support that API, but for pretty much anything that isn't natively supporting, there tends to be an exporter, which is a sidecar process, as you would, that can actually go and hook in. So it can hook in, there's ones for all your favorite databases, MySQL, all these kind of things. And so these things have, HA Proxy has a very rich set of metrics available inside of it. It just happens to be in its own kind of slightly proprietary format. This thing, you can run an exporter alongside of it that hooks into it and then provides that into Prometheus. So Prometheus comes out and scrapes all those things from everywhere. It can even scrape off the Prometheus servers if it wants to. It stores those in its time series database, and then it provides PromQL, so a query language, so that you can go and query those metrics. So that gets you to the same as a lot of the other metric solutions with a slightly different slant on it, that it's coming out and scraping it. But in the world of containers, where you've got containers coming up and down all the time, this is a lot more useful because you can it can automatically discover things that are kind of being added. And it can integrate with other things outside of it. So we run Prometheus monitoring our Kubernetes infrastructure and all of the containers inside of it and the apps in them. But we also use it for stuff that's still running on virtual machines. So a lot of our databases are still running on virtual machines, whilst we've got a lot of our apps running in containers. You can still point this to those virtual machines, maybe using, we use Consul for our general virtual machine service discovery. And so you can still point it at those outside things. You can even hand wire it if you wish to. So it will work both with and without containers, which give it a lot of benefit. But then you can then integrate that with a thing called Alert Manager, which basically what Alert Manager is going to do, and we'll see in a second, is basically it can query a metric, and if a metric is not within some limit or some range, basically a query, if a condition is not held, it can then fire an alert. Right? So if disk space is less than some amount, then fire some alert, and then that alert can go off to all your favorite monitoring. It can wake someone up with a PagerDuty or an email, or it can go out to all of your other favorite monitoring tools. You might have something upstream of this, or you have other traditional monitoring tools. It can go and poke those and tell them whatever's going to wake somebody up, basically, to go and fix the problem. So it has a lot of common integrations. It also has a very simple API that if you want to write a little container microservice that can go and hook it into other things. So we've created one that goes into WebEx Teams. So our WebEx Team Room gets notifications. It was very, very straightforward to write such a thing. And then you can then plug in all your favorite, so it has a UI, but you can also plug in your favorite visualization tools. Typically, a lot of people use Grafana for this kind of metric stuff. So it doesn't try to replace Grafana at all. It has a very basic UI. It looks a bit like this. And you can do queries inside of it, with PromQL. So the query I've asked here is, I want the metrics container memory usage bytes. And this is giving me all of that information, all the numbers, how much usage each of the containers are using. And it's got a whole bunch of labels which are very, very hard to read, but that's fine. Those labels are actually telling me where I got it from. Which host in the cluster was this? So coming back to the kind of, I've got, where is this thing, this container running? Well, this container is running on this particular host. So you can see the host name, I can see the name of the container itself, and a whole bunch of others. So that's the host name. This is like worker 3, worker 2. So I can see which host it's on, but I can also do it on which container it is, or a whole bunch of other things. And so I can then dimension my queries by these sets of labels inside of the solution. And then, as I was saying, you can then create an alert. So these are some alerts here that are kind of looking at the health if a node is down or something else. We have this thing called a dead man switch. I don't know if you're familiar with that. It's basically a way of monitoring the monitoring, that if this alert isn't firing, then you know Prometheus is down. And so you then tend to hook that to a web service in the cloud or something that kind of is waiting. If it doesn't hear from Prometheus for a period of time, it knows that Prometheus is not available. But there are other kind of useful ones here. It's basically saying, instead of monitoring the individual processes, I just want to make sure that all of my pods are up and ready. And if I've asked for 3 pods to run in the cluster, and I've not got 3 pods, I've got 2, but I've got that going on over a period of time, I might fire out an alert saying, well, by the way, your RabbitMQ cluster is not the size that you asked for, which might be an indicator that there's not enough space in the overall Kubernetes cluster, or it might be some other problem. So you can create these rules that are basically doing a metrics query, and then they are firing out through Alert Manager to those tools. And you get nice visualization. So it's a lot of great Grafana dashboards out there on grafana.com that you can just take off the shelf, or you can write your own ones, depending on how familiar you are with those tools. So this is a kind of generic one that you kind of start off with usually, and it sort of shows you an overview of your cluster. How much usage over the whole cluster of the CPU and memory have I got, and file system. But I can see here, these are the individual pods, and I can see how their memory, this is CPU, how their CPU usage is going over time. So I can kind of get a good view of my cluster all in one dashboard. But I might want to kind of drill in, and this is kind of another survival trip. So as well as using something like Prometheus, and I really would highly recommend you look at it, if you're starting to look at containers and microservices. Another survival tip is there is an exporter, so one of these things that Prometheus can scrape. So this is not built into it, but there's into Kubernetes, but one that's available, an exporter called kubestatemetrics. And what that is doing is it's looking at the state of your pods against some other state. So what is this showing me here? So I've actually got a set. It actually happens to be a stateful set, but it's similar to a replica set that we saw, called RabbitMQ. And what I can see across that set is how much usage it's got, right, so overall, but also I can see some statistics about how many I've asked for, how many RabbitMQ pods have I asked for. So you can see the yellow line here, the yellow line here is going along with, this is the desired state. So I asked for 3, and for this whole period, the green and the yellow are matching each other. But at this point, you can see that the green has gone down. What does this mean? Well, something happened at this point, right? I wanted 3, but I've only got 2. And what happened? Well, I just went and kicked the pod. I killed the pod that was running, and then it recovered. Kubernetes then said, well, oh, you've killed me. I'm going to try and go back to the state. And so this is fine. I mean, I don't need to wake anybody up if this happens, because Kubernetes is just doing its job. If this keeps happening over and over again, if I started to see a saw shape, I could write a Prometheus rule that would wake somebody up and say, look, this thing is going up and down over a period of time, that's bad. Or if the amount of time it takes for it to recover is a long period of time. So you can do these metrics queries, time-based ones, to say, look, in the last 5 minutes, if the desired state does not match the actual mistake, fire an alert. And that might be an example. In this case, Kubernetes did as it should have done, and it restarted the pod, and we got back to a good position. But then I actually deliberately scaled down the RabbitMQ cluster to 2. So it was running 3, and my desired state was 2. And you can see here that shortly later, it's shut down and gone down to 2. And why is this not immediate? Well, that RabbitMQ was actually doing a good job and draining off any of the messages that was running through it. So its readiness probe was still, it said, don't send me any more, but I still need to process any in-flight transactions that I've got, and then I'm going to shut down. And so if you've got a badly behaved container, one of these ones that take a long time, you'll see a very long distance between this, and that might give you an indication that somebody needs to go and look at the way in which the life cycle of their containers is working. And there's some other great dashboards in there. This is a really useful one for capacity planning. That can kind of give you an idea of overall how much memory am I using, sort of similar to the original one, but it just helps you plan, because what you typically find is you start a whole bunch of containers up, and then your whole Kubernetes cluster is swamped because you only gave it 2 nodes and there's not enough space for all the requests and the request and limits that we talked about, those C groups, for it to get spread across the cluster. So this is another really useful dashboard. I found this one very recently, and I was like, oh wow. did I not know about this one? So there's a lot of really good out-of-the-box visualizations that you can then use also to create rules. But also, I would certainly recommend, for anyone who's trying to build microservices, start leveraging some of the common frameworks. So there are frameworks for Go, there's frameworks for Java like Spring and so on that provide you a whole bunch of these things out of the box. So actually with Spring, which is a Java framework, it automatically gives you service discovery, it automatically gives you Prometheus metrics, API, so you can directly work with it. So a lot of these frameworks are providing all of this other stuff, and this gives you a lot of help. So there's like distributed tracing. When you've got all these microservices talking to each other over a network, you kind of need to have some way of tracing those API calls. And so leveraging a framework instead of getting every single application to try and do this independently, it's going to help you a lot. And so that's what we've done. We've actually got frameworks in Go that we've used that are open sourced. We've got ones that we've written for Node.js and so on. And they just kind of give you a common way of doing these things and getting health and metrics and diagnostics across all these microservices and containers. So that's the monitoring containers section. So, again, my survival tips, you need to start transitioning away from host-based monitoring to app ones, and Prometheus is a great option to do that. I certainly would highly recommend it. Look at your alerting driven from metrics. Use the kube state metrics as well. It's a really, really useful tip. I actually got this from one of our customers, told me to use it, and I was really thankful, so I'm sharing his tip. But leverage some frameworks as well. So any questions on the metrics, Prometheus? Nope. Okay, great. So just to conclude, what we've gone through today is really how to survive containers world, right? So remember, this was all us going to containers world with kids, right? And so this is the same as going to Disney World with kids. You need to prepare, right? And we went through the preparation steps of getting there, understanding the reasons, the drivers. We talked a lot about that. Apply and document those good practices that I went, and there's many more that you can find, but do that and look to continuously improve on what you're doing. So don't just sort of say, well, okay, I'm lifting and shifting and that's it, I'm done. Try to continuously improve on those things. You need to tool up, so you need to understand how the containers work. We've went through a lot about, how the C groups, the namespaces, all that kind of things. Get familiar with debugging containers, some of those things that we will go and do those things. Go try out the TCP dump of a container, and of course learn about IP tables. And then in terms of metrics, getting your metrics, start moving towards that app-centric monitoring. Prometheus for the win, definitely. I can't recommend it more. It's definitely an excellent choice for this kind of environment. But also, things like calls and call flows and timing, get some of that information out of those metrics. Start looking at those kind of things. As I said, we've got a WebEx team room that you can join through the app. So if you've got more questions, you want to engage with me, I've been doing this for quite a while, getting things into production, containers into production, so I'm happy to continue to share that information after the session. I'd really appreciate if you could complete your, so I know everybody's asked you to do this, but I'm going to really ask you to do it. You just go into your app, into your profile, and then just scroll down to My Surveys. It's very straightforward, or you can do it on the website. All you need to do is just go through, you go excellent, 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 put a comment, and then you're done. That's all you need to do. No, but seriously, I really appreciate your feedback. So it really does help us keep this event going. There's a couple of things to continue. There is another day of the conference. So after the party, tonight everyone looking forward to the party. We're not going to Disney World, but Universal's cool as well. So tomorrow morning, you can learn a lot more if you can get up for 8 still, but if you can get up for 8, or you can watch this on the playback if you are feeling a bit queasy in the morning. We'll see. It depends on how many roller coasters you go on. There's a great session that kind of takes what we've been doing in containerizations in the video space and going through that in a lot more detail. So that's tomorrow morning. There's a couple of great things. If you want to find out more about Prometheus and Grafana, there's a dev night workshop, so I certainly recommend going along that. If you've not had a go, it's a great way of kind of getting hands-on and understanding about what it does. And there's another thing at the World Solutions Theatre talking about production-grade Kubernetes in a multi-cloud world. And if you haven't been to the Embrace a Multi-Cloud World section of the Cisco campus, Cisco area, then there's a couple of demos there. One on Cisco Cloud Services, which is sort of bringing a lot of these things together, and some stuff there on the Cisco Container Platform as well, which is some of the things we talked about before. And that's it, really. You know, as I said at the beginning, taking microservices is like, into production is like visiting Disney World with kids, and now hopefully you'll all have a survival guide to do that. Thank you very much.